Good afternoon and welcome to this week's IGC Events webinar, Focus on Geothermal, which is presented by Think Energy and Enerchange. My name is Anne and today I am pleased to welcome Ludwig Irrgang of the Technical University of Munich. Ludwig has a master's degree in energy and process technology. During his studies, he worked as a student trainee at EVA Fahrzeugtechnik GmbH in the areas of electromobility and stationary energy storage systems, and as a part-time employee in the areas of system administration and quality management. After graduating, he started at the Technical University of Munich as a research assistant at the Chair of Energy Systems. Here, he is involved in projects such as Decagon, modeling of air condensers for ORC processes, or FlexGeo, innovative geothermal energy systems, as well as experimental activities such as the construction of the test bench GeoReach. With today's presentation, Ludwig will talk about geothermal reversible absorption chillers, unlocking the full potential of geothermal energy for district heating and cooling. This presentation examines the potential use of absorption technology in the field of geothermal energy. It offers a brief overview of various absorption cycles, namely chiller, heat pump, and heat transformer, and demonstrates how these three modes of operation can be combined within a single system. The GeoReach test rig will be introduced and the planned experimental activities will be outlined. We are looking forward to an interesting presentation. Ludwig, the floor is yours.
Yeah, thank you very much for this nice introduction and thank you all for joining in today's webinar. I'm happy to talk in the next 25 minutes about our research at the Chair of Energy Systems. And yeah, to give you a short outlook over the structure of today's webinar, I want to start briefly with the geothermal resource, since I'm sure you all know a lot about geothermal energy in general. Then I want to talk about why we want to use absorption technology in combination with the geothermal resource and give some fundamentals of the absorption heat pumps and heat transformers to give you a chance to understand what we want to do with the test rig. And then I want to give a short conclusion, and I hope we have a vivid discussion afterwards. Maybe just a quick word regarding our research group at the Chair and also myself. I started roughly 3 years ago at the Chair of Energy Systems, and from the beginning I was mainly involved with building an absorption chiller test rig for geothermal energy use. And this concept I'm presenting today developed over the last years, and since 1.5 years now, we started building the test rig that we're now commissioning. Other than that, we also have a lot of expertise regarding organic Rankine cycles and high temperature heat pumps, which are also oftentimes used in combination with the geothermal energy. We also do a lot of district heating and cooling network simulation, and also look into the area of CO2 plume geothermal use. Yeah, the geothermal resource, if I'm talking about the geothermal resource today, I'm mostly referring to the South German molasses basin, which can be regarded as the hotspot of the geothermal potential in Germany, with a lot of projects being realized there. We have a large temperature range in this area, starting from 65 degrees up to 150 degrees. So the boundary conditions for our research are to look at all these different temperatures and evaluate what kind of absorption technology can be used. Maybe some words about unique characteristics of the geothermal heat use. I think 2 things are important. First, the reinjection temperature is not affecting the production temperature, which just means that lower reinjection temperatures increase the geothermal heat use and decrease specific cost and specific emissions, for example. And in my understanding, this means that we have to reduce reinjection temperatures. And today I want to show you how we can do that with absorption technology. Typical projects in the SMB look like the picture on the right. We usually have, of course, district or direct heat use. Then we have sometimes electricity generation if the temperatures are high enough. And also in some places we already have cold production with absorption, or in some cases adsorption chillers. Why do we have this cold production in combination with geothermal energy? As you can see on the right, depending on ambient temperatures, we have different heat and cold demands over a year's period, which means that in summer we have very low heat demand, which translates to very low geothermal heat use, but we have high cold demand. And this means that we can use the geothermal heat for cooling. And in contrast to the heat demand, which might potentially decrease with better insulation technology, heat demand is expected to rise in the upcoming years. And yeah, I want to stress that just because it's very relevant right now with the current heat wave that we have in Europe. On the left, you can see general trends regarding global and European temperature increase. And on the right, you can see some newspaper articles regarding the current heat wave. And yeah, I think this emphasizes in two ways why we will have increased cooling demand. On the one hand, of course, we have rising temperatures. That means that a lot of office building and also residential houses will include AC units in the future. But I think these heat waves also motivate people to get some kind of air conditioning system just to increase the comfort level. And yeah, I can feel it myself in the office building right now. I think the ideas of getting AC units will become more common in Europe in the future. Why use absorption technology in combination with geothermal energy? As I said, we can use the geothermal heat for cold production and simultaneously use very low electricity for the cold production. That means that on the one hand, we increase the additional revenue for the geothermal project, which is good for the economics. On the other hand, we reduce the consumption of other energy sources for cooling. And with the current German electricity grid, for example, we also would decrease CO2 emissions by using geothermal energy. If we want to compare compression chillers with absorption chillers energetically, for example, we also have to look at higher cooling loads for the absorption chiller and consequent higher electricity load for cooling. But I think, to be fair, we also have to include the additional pump work of the geothermal source. But still, we did analysis in a recent paper, which will be published soon in the International Journal of Refrigeration, where we looked at the comparison of compression chillers to all kinds of absorption chillers. And we found that absorption chillers are still energetically superior, and also that the single effect cycle is the most relevant for the typical geothermal boundary conditions. In the future, we also will publish results on economic and environmental analysis regarding compression versus absorption chillers, but there I have to advise you to future publications. We're not the only one that realized that geothermal cooling is a good idea. That's why there are all kinds of different projects already realizing geothermal cooling. One example would be the city of Munich in Germany, with Germany's largest district cooling project and 8.2 megawatts of geothermal cooling in the city center. Another example would be Masdar City in Abu Dhabi, where they satisfy 10% of the cooling load with a production temperature of 90 degrees at 100 liters per second. And what I also found in researching for this presentation is, for example, that for the Paris Olympic, they also did the district heating and cooling for the Olympic Village with geothermal energy. So very interesting, I think. Apart from geothermal heat use, I think absorption chillers have some other advantages in comparison to compression chillers. The main disadvantages would be that absorption chillers have higher investment costs, and maybe in high load fluctuation, they might be not as flexible. On the other hand, operating costs can be reduced a lot if we have cheap heat available, and usually absorption chillers are quite reliable since there are no compressors and no moving parts like a compression chiller. And also regarding, for example, working fluids, absorption chillers have better sustainability since they do not have any geothermal warming potential, ozone depletion potential, or they are not affected by the PFAS regulations. So you might ask, where's the need for research and why do you even look at this if it's so good? Yeah, we identified one problem. Since absorption chillers are quite investment intensive and they are only operated during the high cold demand hours, we have very low yearly operating hours, or we could have higher yearly operating hours of the machine. And yeah, if we look again at the heat demand and cold demand curves, we can identify another problem with geothermal energy. that we have very high peak load in winter times, and usually these peak loads have to be covered with other energy sources, for example, fossil fuels. And that's where we can also use absorption technology, for example, absorption heat pumps or heat transformers, to increase the heat production from the geothermal brine, and this way also increase revenue and decrease the consumption of, for example, fossil fuels. So to summarize a little bit the motivation, we have a rising cold demand and a low geothermal use in summer, which leads us to the conclusion that geothermal cooling could be a good idea or alternative to conventional compression chillers. Absorption chillers, although they are very investment intensive, can only be operated during a few hours in the summer months, and we simultaneously have winter peak heating demand. And yeah, that's where we see a possibility for a special absorption machine which can operate during both seasons, maximizing the operating hours and also maximizing the heat output and the productivity of the geothermal resource. So the question remains, how would such a machine look like? And to discuss that, I want to go a little bit into the fundamentals of absorption cycles. So what we see here is the absorption chiller cycle. Usually we use lithium bromide water as a working fluid for refrigeration purposes, since it gives us the highest efficiencies. With the cycle, we produce cold by evaporating water at very low pressures, and we can use heat as the main driving energy. On the right, you see the thermal compressor. I mean, generally, this looks very similar to a classical compression heat pump or compression chiller cycle, but instead of the compressor, we have this thermal compressor. That means that we use heat as driving energy, but we don't have to use a lot of electrical energy because we have this pumping process instead of a compression process. The efficiency of the whole cycle is usually measured as the useful cold output in the evaporator in comparison to the heat input at the desorber, and it's usually around 0.7 to 0.8. I want to note that you should not compare that directly to the EER of a compression chiller, because that would give the absorption chiller an unfair disadvantage. What we use here as input is heat, or maybe even low temperature heat. And on the other hand, the compression chiller uses electrical energy, which is pure exergy. So we should never compare the EER directly to the COP, and we will later see how one translates into another. To give you a more practical understanding, if we would have, for example, 100 liters per second at 100 degrees and use just 10 degrees of the brine temperature for the absorption chiller, we can already produce a cooling output of almost 3 megawatts. And if you look at the classical compression chiller with an EER of 3.5, we would use 840 kilowatts for the same cooling output. So there you can see that a lot of geothermal projects have the potential to produce high amounts of cold and thereby save a lot of electrical energy. As you can see, we have the heat rejection at condenser and absorber. That's what I mentioned earlier, that in comparison to a classical compression chiller, we have additional heat output, and that should always be considered when installing an absorption chiller. The absorption heat pump, on the other hand, it looks very similar to the absorption chiller. It's essentially the same cycle. The difference is that we use the condenser and the absorber heat output as the useful heat fluxes. And since the temperatures are generally higher in this cycle, we will use even higher temperature heat as the main driving energy. And the nice thing now about the heat pump is that we can extract additional heat from the geothermal brine just before reinjection with the evaporator. The efficiency is calculated with the useful heat at condenser and absorber in relation to high temperature heat input, and is usually around 1.6 to 1.7. In a practical example, it would look like this. The high temperature heat input in most cases would not come from geothermal, but from other heat sources, for example, fossil fuels, biomass, waste heat. And imagine we have a peak load of 8 megawatts that we have to cover. And now we can only use 5 megawatts from the fossil fuel, for example, to get 8 megawatts of heat output. And That's because we can extract additional 3 megawatts with the evaporator from the geothermal brine. And that would translate to a reduction of fuel consumption of around 37.5% and a reduction in reinjection temperature at 50 liters per second, that would be 14.2 degrees Celsius, and at 100 liters per second, it would be 7.1 degrees Celsius. So this technology might be very interesting for projects where we have fossil burners right now, which are used to cover peak loads. So that's why we look also into that. But as you can see, if we want to use the heat pump solely with geothermal energy, we have to have very high production temperatures. And yeah, that means that the absorption heat pump is more relevant for these projects where we have also other heat sources. I want to mention another technology here, the absorption heat exchanger, which might be more interesting and is pretty similar to absorption heat pump cycle and uses an additional heat exchanger. I think if you want to understand it in detail, you have to look at it additionally. But essentially, you have heat exchange with a pinch point violation, and it allows you to extract more heat from the geothermal brine. But there again, the feasibility depends on the geothermal temperatures, on the network temperatures. So we have kind of the same problem. So what we identified as an alternative for geothermal heat use is the absorption heat transformer. And the cycle is shown here. Essentially, the process is reversed, which means that we have an additional refrigerant pump in the refrigerant cycle. And with the cycle, we can produce high temperature heat output with the absorption process. So the output heat is at the higher temperature than the heat we gave to the cycle in the first place. So we can input heat at evaporator and desorber at the lower temperature, and then use the absorber heat, for example, for the district heating network. We also have the condenser, which rejects heat to the ambient. But the good thing is that this condensation process is influenced in a good way if we have low ambient temperatures. So if we want to use the cycle in winter times, the low temperatures are very beneficial. The efficiency here is calculated as the absorber heat output to the heat supplied in evaporator and desorber, and peaks at around 0.5. If we have an example for the absorption heat transformer, we could look at such a setup where we have a reinjection temperature of 75 degrees, for example, without the heat transformer. And with the heat transformer, we could reduce the reinjection temperature, let's say 20 degrees. That would mean that half of the heat that we extracted from the geothermal brine can now be used for the district heating. So we extracted 8.4 megawatts and can use 4.2 megawatts for the district heating. Of course, we have to have the heat rejection. On the other hand, if you want to use this reversible machine in summer and winter, we have to have heat rejection for the absorption chiller anyway. So this would also be in place already. And a setup would look like this. We have the production well with 100 degrees production temperature, then the district heating heat exchanger cooling down the brine to 75 degrees, and then additional cooling of 20 degrees with absorption heat transformer. This could also be interesting for projects where we have very low temperatures in the first place and want to upgrade heat to our useful temperature level. So we identified the heat transformer as a very interesting technology for geothermal energy, also because the low ambient temperatures in winter benefit the cycle and the heat rejection. So what we wanted to investigate is how can we combine an absorption chiller and an absorption heat transformer into one machine. And that's where the concept for our test rig came from. So GeoReach, which is the name of the test rig, stands for Geothermal Reversible Absorption Chiller. And as I explained, we want to have the chiller mode in the summer operation, and the heat pump, or the focus is more on the heat transformer mode and winter operation. Yeah, we designed the machine for 100 kilowatts of cooling output. And the idea is to demonstrate the reversible concept, which means that we have the chiller in the summer months and the heat transformer in the winter months. And the difficulty there is that we have to reverse the cycle, as you saw. The one cycle goes in the left direction and the other one in the right direction. We also want to use the experimental results to identify design guidelines and control strategies for geothermal energy in general. So how can we design absorption chillers, absorption heat pumps, or heat transformers for geothermal energy? And how can we control the machines in an optimal way? And we want to identify the temperature boundaries for the different uses. So which network temperature needs what kind of heat source temperature, for example. I want to shortly go over the innovative ideas that we realized in the machine. So for the construction and design, we have a partner, which is Ecorima. They are a very young absorption chiller and heat pump company. And so they allowed us to have a lot of changes in the lookout of the machine. So that's what I want to show now. We have a symmetrical design of the two pressure stages, which are good for the reversible operation. And for the heat pump mode, we included controllable valves between the two pressure stages, because we will have very different pressures in the high and low pressure part, and we have to control for the pressure. We have access points for solution and refrigerant analysis, which in the long run we want to use to have automated solution and refrigerant control. And for the heat transformer mode, we already included a drip tray system in the condenser, which will be used as an evaporator in the heat transformer mode. And we have additional piping to include the additional pump in the refrigerant part, and also the additional piping which we need to realize the heat transformer mode. For the external hydraulics, we simulate the geothermal heat source with an additional external circuit. So we have the heat source and then another circuit. This way we want to simulate different desorber temperatures with different geothermal source temperatures and find optimums, because it's always a trade-off between how far do we cool down the geothermal brine and how the absorption heat pump generate. We have 200 kilowatts of heating at a maximum temperature of 140 degrees, which can simulate the boundary conditions of a typical geothermal project very well. For the heatsink, we designed to do parallel cooling of condenser and absorber for optimal chiller operation, but also mainly because we want to prepare for the heat pump and heat transformer operation. Here are some pictures of the machine internals when they were delivered from the manufacturer. As you can see, it's a quite compact machine for the 100 kilowatts of cooling. We have used stainless steel for most of the parts, since we want to have reliable operation and don't want to be stressed about too much corrosion issues. And yeah, that's how it looks right now. All the external piping done, all the sensors and pumps included. And so right now we are working in the commissioning phase to implement the last steps of the control system, to test the external hydraulics, and to, as you can see, apply heat insulation, which is missing right now. And so we plan to start operation in the next month, and the first experimental results should be available until the end of the year. We start with the chiller operation also to get a feel for the machine, and then next year we want to do the heat pump experiments and demonstrate the reversible concept when we understand a little bit more about how the machine works, and then we will do the reversible concept next year. Okay, the main takeaways, I think, for this presentation. I think geothermal energy is a very unique case for absorption technology. I think geothermal cooling is a sustainable alternative to conventional compression chillers. Absorption heat transformers could be very interesting for geothermal projects, since they just increase the heat availability without additional energy input. And a reversible absorption chiller, which combines these two operation modes, I think would be very interesting for the geothermal industry. We hope that the reversible concept will be demonstrated with our test rig. So stay tuned for our updates, and thank you very much for your attention, and I'm looking forward to your questions.
Perfect. Thank you for your presentation. And just a quick reminder, our Praxis Forum is happening soon and we would like to see you there. Let's start with the questions. So everybody can just write their questions in the chat and I will read them. So the first one is, why are the investment costs so high?
It depends a little bit on what absorption technology we look at, but for classical lithium bromide water absorption chillers, we look at around 1,000 euros per kilowatt. And the difference is, as you saw, these machines are quite heavy and use a lot of material. And that's comparison, a 100 kilowatt compression machine would be way smaller. And yeah, maybe also a factor is that the compression industry maybe has a higher output and therefore lower specific prices. Yeah, but that's just how it is. I mean, it's not an order of magnitude. I think large compression systems are around 250 to 400 euros per kilowatt, but there's a difference. And what you also have to include is that you have to have a larger heat rejection system, which also adds to the increased investment cost.
Okay, perfect. Thank you. And could you just repeat the advantages for absorption chillers for cooling and heating?
The advantages for cooling and heating, I think, do you refer to the table I showed? I mean, for cooling, it's quite obvious. If we can use the geothermal heat, which is already available, we save the electricity price. And that means that on the one hand, the geothermal project can sell another product and increase the revenue, and maybe also decrease the price for the heat consumer in winter times. And on the other hand, of course, we save on electricity cost. Maybe, I mean, it's quite obvious too. If we decrease the heat output of the geothermal project with the heat transformer, for example, we also just can sell more heat, which also makes more revenue or decreases cost for the end consumer.
Okay. Then there's a comment that it is a very important technology, and if there is a paper available on the subject.
Yeah, we're working on several papers right now. You can go to my ResearchGate page maybe and look at the papers from our research group. And we recently published a paper with colleagues from Singapore, for example, where we looked at LCA analysis of geothermal cooling. It's more about geothermal cooling in the Asian area, so not so relevant maybe for Europe. Yeah, as I said, I'm publishing another paper shortly regarding the energetic comparison of compression systems with geothermal cooling, also including cascaded cycles and hybrid cycles. And yeah, in the next 2 years, we will also publish economic and environmental analysis of geothermal cooling systems. So if you just stay tuned to my LinkedIn page, I think you might get updates. Otherwise, maybe write me an email, then I can give you a larger list.
Perfect. Then another one is, can thermal storage tanks be integrated with the system for load balancing purposes?
I mean, probably referring to cooling storage. I think storage makes sense over a days period, let's say. I think at the normal temperatures we have with these machines above 0 degrees Celsius, yeah, cold storages become very large very quickly. So realistically, I would say we can balance the load between night and day a little bit. And what's a benefit also is that usually in the night we have lower ambient temperatures, which benefits the absorption chiller. So yeah, it might be interesting to add cold storage with absorption chillers just to take advantage of these nightly low ambient temperatures. But I think on a seasonal basis, storages would just be way too large.
Okay, I think the next question is kind of connected to the first one. So the possible usage of absorption chillers in hot, dry climates has the issue of cooling down the condenser. This because the air temperature is too high for air coolers and the underground water is at 30 to 35 degrees, making it hard to cool down the condenser. How do you believe it's possible to overcome this issue in the next years?
I mean, of course, that's a highly depending on the different boundary conditions. If we have high enough source temperatures, we can tolerate also high ambient temperatures. But yeah, that's one thing which we want to examine with the experiments. What is the influence of the ambient temperatures on the necessary heat source temperatures that we need to have in order for the machine to cover a certain load? One idea would be to have some kind of cold storage, for example, and use the low temperature in the night. In Munich, I know that they use river water to cool down the absorption chillers, but in most cases, I think there is no river available to take these cooling loads. For very large systems, also cooling towers, wet cooling towers, what might be interesting. I think that's a very interesting discussion because it also influences a lot the electrical consumption that we have for the absorption chillers. And what we see is that high electrical consumption for the heat rejection are really influencing the overall efficiency of the system. And we also see that, for example, with double lift cycles, where you could think, okay, we can tolerate lower source temperatures, we have very high cooling loads, which leads to low efficiencies in comparison to the compression chiller. So yeah, that's a very interesting discussion. But yeah, I don't think I can give you a definite answer on that.
Okay, then there's another comment. Thanks for the interesting presentation. Looking on 150 degrees absorption heat pump usage, at Steps Ahead, we have realized a couple of heat pumps projects using 105 degrees as driving heat for biomass district heating systems. So I think that's just a comment. Then there's another question, how fitting this technology would be for our regions for cooling. You already talked about this. I don't know if you want to add something.
Yeah, our regions, I don't know where you come from, but yeah, I think as we can see with the examples of the cooling projects, there's more or less a potential all around the globe, probably even more in hotter climates where you don't need the geothermal heat for heating purposes. I think there the cooling with geothermal energy might be an even bigger topic. And yeah, that's also why we want to have this reversible chiller, because maybe in our climate conditions, the investment decision to buy an absorption chiller is influenced if we can also produce additional heat. But yeah, I think there's a potential all around the globe and probably also where you come from.
And then another comment to the cold storages. There are many clients that have large sprinkler tanks. Yeah, just.
Yeah. Yeah, actually, we have some industry partners where we did some system studies, and we see that sprinkler tanks can be a very interesting way to store cold. Yeah, because they're in most industrial or office buildings, you have them anyway. But yeah, I'm not an expert on this issue, but I think there may be some security issues there. Maybe there are temperature limits. But I think for energy storage in general, sprinkler systems are very, very interesting. No, thank you for the comment.
And the last question for today, how small can the absorption chiller be? Are they only for large spaces?
Yeah, also a good question. We have 100 kilowatts now, which still fits into an elevator. But if you look at, for example, camper vans or hotel rooms, they also use absorption chillers in their refrigerators. There might be other reasons to use absorption chillers. In the hotel room, for example, it's the noise emission, which is just lower with absorption chillers. So they might go down to a few 100 watts. So there's no limit to how small or large such a system can be. I mean, we have systems with over 10 megawatts, and then I think down to a few hundred watts probably.
Okay, good. Then I would like to thank you all for this nice discussion. It's a very important topic. And thank you, Mr. Irrgang, for the very insightful presentation. And I wish you all a good weekend.
Thank you very much.